Introduction to Process Control, Chapter 1, 1.1 Introduction. When observing a chemical process in a plant or laboratory, one sees flow surging from vessel to vessel, liquids bubbling and boiling, viscous material being extruded, and all key measurements changing continuously, sometimes with small fluctuations, and other times in response to major changes. The conclusion immediately drawn is that the world is dynamic. The simple and obvious statement provides the key reason for process control. Only with an understanding of transient behavior of physical systems can engineers design processes that perform well in the dynamic world. In their early training, engineering students learn a great deal about the physical system of steady states, which is natural because steady state systems are somewhat easier to understand and provide an appropriate learning examples. However, the practicing engineer should have a mastery of dynamic systems as well, and this book provides the basic information and engineering methods needed to analyze and design plants that function well in a dynamic world. Control engineering is an engineering science that is used in many engineering disciplines, for example chemical, electrical, and mechanical, and it is applied to a wide range of physical systems from electrical circuits to guided missiles to robots. The field of process control encompasses the basic principles most useful when applied to the psychochemical systems often encountered by chemical engineers, such as chemical reactors, heat exchangers, and mass transfer equipment. Since the principles covered in this book are basic to most tasks performed by chemical engineers, control engineering is not a narrow specialty but an essential topic for all chemical engineers. For example, plant designers must consider the dynamic operation of all equipment because the plant will never operate at steady state with time derivatives exactly equal to zero. Engineers charged with operating plants must ensure that the proper response is made to the ever-occurring disturbances so that the operation is safe and profitable. And finally, engineers performing experiments must control their equipment to obtain the conditions prescribed by their experimental design. In summary, the task of an engineer is to design, construct, and operate a physical system to behave in a desired manner, and an essential element of this activity is sustained maintenance of the system at the desired conditions, which is process control engineering. And as you might expect, process control engineering involves a vast body of materials, including mathematical analysis and engineering practice. However, before we can begin learning the specific principles and calculations, we must understand the goal of process control and how it complements other aspects of chemical engineering. This chapter introduces these issues by addressing the following questions. What does a control system do? Why is control necessary? Why is control possible? How is control done? Where is control implemented? What does control engineering engineer? How is control process documented? And what are some sample control strategies? 1.2. What does a control system do? First, we will discuss two examples of control systems encountered in everyday life. Then we will discuss the features of these systems that are common to most control systems and are generalized in definitions of the terms control and feedback control. The first example of a control system is a person driving an automobile, as shown in Figure 1.1. The driver must have a goal or objective. Normally, this would be to stay in a specific lane. First, the driver must determine the location of the automobile, which she does by using her eyes to see the position of the automobile on the road. Then, the driver must determine or calculate the change required to maintain the automobile at its desired position on the road. Finally, the driver must change the position of the steering wheel by the amount calculated to bring about the necessary correction. And by continuously performing these three functions, the driver can maintain the automobile very close to its desired position as disturbances like bumps and curves in the road are encountered. The second example is the simple heating system shown in Figure 1.2. The house in a cold climate can be maintained near a desired temperature by circulating hot water through a heat exchanger. The temperature in the room is determined by a thermostat, which compares the measured value of the room temperature to a desired range, say 18 to 22 degrees Celsius. If the temperature is below 18 degrees Celsius, the furnace and pump are turned on, and if the temperature is below 22 degrees Celsius, the furnace and pump are turned off. If the temperature is between these two ranges of degrees of Celsius, the furnace and pump statuses remain unchanged. A typical temperature history in a house is given in Figure 1.3, which shows how the temperature slowly drifts between the upper and lower limits. It also exceeds the limits because the furnace and heat exchanger cannot respond immediately. This approach is termed on/off control and can be used when precise control at the desired value is not required. We will cover better control methods, which can maintain important variables much closer to their desired values later in this book. Now that we have briefly analyzed two control systems, we shall identify some common features. The first is that each uses a specific value or range as a desired value for the controlled variables. When we cover control calculations in Part 3, we will use the term set point for the desired value. Second, the conditions of the system are measured. That is, all control systems use sensors to measure the physical values and variables that are to be maintained near their desired values. Third, each system has a control calculation or algorithm which uses the measured values and their desired values to determine a correction to the process operation. The control calculation for the room heater is very simple, on/off, whereas the calculation used by the driver may be very complex. And finally, the results of the calculation are implemented by adjusting some item of equipment in the system, which is termed the final control element, such as the steering wheel or the furnace and pump switches. These key features are shown schematically in Figure 1.4, which can be used to represent many control systems. Now that we have determined and discussed some common control systems and identified key features, we shall define the term control. The dictionary provides the definition for the verb control as to exercise directing influence. We will use a similar definition that is adapted to our purposes. The following definition suits the two physical examples and the schematic representation in Figure 1.4. Control is a verb to maintain desired conditions in a physical system by adjusting selected variables in the system. The control examples have an additional feature that is extremely important. This is feedback, which is defined as the following. Feedback control makes use of an output of a system to influence an input to the same system. For example, the temperature of the room is used through the thermostat on/off decision to influence the water heater flow to the exchanger. When feedback is employed to reduce the magnitude of the difference between the actual and desired values, it is termed negative feedback. Unless otherwise stated, we will always be discussing negative feedback and will not use the modifier negative. In the social sciences and general vernacular, the phrase negative feedback indicates an undesirable change because most people do not enjoy receiving a signal that tells them to correct an error. Most people would rather receive positive feedback, a signal telling them to continue a tendency to approach the desired condition. This difference in terminology is unfortunate because we will use the terminology for automatic control with negative, indicating a change that tends to approach the desired value throughout the book without exception. The importance of feedback in control systems can be seen by considering the alternative without feedback. For example, an alternative approach for achieving the desired room temperature value would set the hot water flow based on the measured outside temperature and a model of the heat loss of the house. This type of positive approach, termed feed forward, will be encountered later in the book, where its use in combination with feedback will be explained. The strategy without feedback would not maintain the room near the desired value if the model had errors, as it always would. Some causes of model error might be changes in external wind velocity and direction of inflows or air through open windows. On the other hand, feedback control can continually manipulate the final element to achieve the desired value. Thus, feedback provides the powerful feature of enabling a control system to maintain the measured value near its desired value without requiring an exact plant model. Before we complete this section, the term input and output are clarified. When used in discussing control systems, they do not necessarily refer to material moving into and out of the system. Here, the term input refers to a variable that causes an output. In the steering example, the input is the steering wheel position and the output is the position of the automobile. In the room heating example, the input is the fuel to the furnace and the output is the room temperature. It is essential to recognize that the input causes the output and that this relationship cannot be inverted. The causal relationship inherent in the physical process forces us to select the input as the manipulated variable and the output as the measured variable. Numerous examples with selections of controlled and manipulated variables are present in subsequent chapters. Therefore, the answer to the first question about the function of control is, a feedback control system maintains specific variables near their desired values by applying the four basic features shown in Figure 1.4. Understanding and designing feedback control systems is a major emphasis of this book. 1.3. Why is control necessary? A natural second question involves the need for control. There are two major reasons for control, which are discussed with respect to the simple stirred tank heat exchanger shown in Figure 1.5. The process fluid flows into the tank from a pipe and flows out of the tank by overflow. Thus, the volume of the tank is constant. The heating fluid can be changed by adjusting the opening of the valve in the heating medium line. The temperature in the tank is to be controlled. The first reason for control is to maintain the temperature at its desired value when disturbances occur. Some typical disturbances for this process occur in the following variables: inlet process fluid flow rate and temperature, heating fluid temperature, and pressure of the heating fluid upstream of the valve. As an exercise, you should determine how the valve should be adjusted, opened, or closed in response to an increase in each of these. The second reason for control is to respond to changes in the desired value. For example, if the desired temperature in the stirred tank heat exchanger is increased, the heating valve percent opening would be increased. The desired values are based on a thorough analysis of the plant operation and objectives, and this analysis is discussed in Chapter 2, where the main issues are arranged in 7 categories. 1. Safety. 2. Environmental protection. 3. Equipment protection. 4. Smooth plant operation and plant production rates. 5. Product quality. 6. Profit optimization. 7. Monitoring and diagnosis. These issues are translated to values of variables, temperature, pressure, flow, and so forth, which are to be controlled. 1.4. Why is control possible? The proper design of plant equipment is essential for control to be possible and for control to provide good dynamic performance. Therefore, the control and dynamic operation is an important factor in plant design. Based on the key features of feedback control shown in Figure 1.4, the plant design must include adequate sensors of plant output variables and appropriate final control elements. The sensors must respond rapidly so that the control action can be taken in real time. Sensors using various physical principles are available for the basic process variables, flow, temperature, pressure, and level, for composition, mole fraction, and physical properties such as density, viscosity, and heat of combustion. Many of these sensors are inserted into the process equipment with a shield protecting them from corrosion effects of the stream. Others require a sample to be taken periodically from the process, and note that this sampling can be automated so that the new sensor results is available at frequent intervals. The final control elements in chemical processes are usually valves that affect fluid flows, but they could be other manipulated variables such as power to an electric motor or speed of a conveyor belt. Another important consideration is the capacity of the process equipment. The equipment must have a large enough maximum capacity to respond to all expected disturbances and changes in desired variables. For the stirred tank heat exchanger, the maximum duty, as influenced by temperature, area, and heat medium flow rate, must be large enough to maintain the tank's temperature for all anticipated disturbances. This highest heat duty corresponds to the highest outlet temperature, the highest process fluid flow, the lowest inlet fluid temperature, and the highest heat loss to the environment. Each process must be analyzed to ensure that adequate capacity exists. Further discussion of this topic appears in the next two chapters. Therefore, the answer to why control is possible is that we anticipate the expected changes in plant variables and provide adequate equipment when the plant is designed. The adequate equipment designed for control must be calculated based on expected changes. Merely adding extra capacity, say 20%, to equipment sizing is not correct. In some cases, this would result in waste. In other cases, the equipment capacity would not be adequate. If this analysis is not done properly, or changes outside the assumption occur, achieving acceptable plant operation through manipulated final control elements may not be possible. 5. How is control done? As we have seen in the automobile driving example, feedback control by human action is possible. In some cases, this approach is appropriate, but in the continuous, repetitive actions are tedious for a person. In addition, some control calculations are too complex or must be implemented too rapidly to be performed by a person. Therefore, most feedback control is automated, which requires that the key functions of sensing, calculating, and manipulating be performed by equipment and that the element communicate with other elements in the control system. Currently, most automatic control is implemented using electronic equipment, which uses levels of current or voltage to represent values to be communicated. As would be expected, many of the computing and some of the communication functions are being performed increasingly often with digital technology. In some cases, control systems uses pneumatics, hydraulics, or mechanical mechanisms to communicate and calculate. In these systems, the signals are represented by pressure or physical position. A typical process plant will have examples of each type of instrumentation and communication. In the control room, an individual is responsible for monitoring and operating a section of a large complex plant containing up to 100 controlled variables and 400 other measured variables. Generally, the plant never operates on an automatic pilot. A person is always present to perform tasks, not automated, to optimize operations and to intervene in the case of unusual or dangerous situation occur, such as equipment failure. Naturally, other people are present at the process equipment, usually referred to as in the field, to monitor the equipment and to perform functions requiring manual intervention such as backwashing filters. Thus, well-automated chemical plants involve considerable interaction between people and control calculations. Other control configurations are possible and are used when appropriate. For example, small panels with instrumentation can be placed near a critical piece of process equipment when the operator needs to have access to the control system. While introducing some process adjustments, this adjustment would not prevent the remainder of the plant from being controlled from a central facility. Also, many sensors provide a visual display of the measured value, which can be seen by the local operator, as well as the signal transmitted to the central control room. Thus, the local operator can determine the operating conditions of a unit, but the individual local displays are distributed around the plant, not collected in a single place for the local operator. The short answer to the location question is 1. Sensors, local indicators, and valves are in the process. 2. Displays of all plant variables and control calculations are in a centralized facility. It is worth noting that the increased use of digital computing makes the distribution of the control calculation to the sensor locations practical. However, all controllers would be connected to a computing network that would function like a single computer for the purposes of the material of this book. 1.7. What does control engineering engineer? What can engineers do so that a plant can be maintained reliably and safely near desired values? Most of the engineering decisions are introduced in the following 5 topics: process design, measurements, final elements, control structure, control calculations. Process design. A key factor in engineering is the design of a process so that it can be controlled well. We noted in the room heating example that the temperature exceeded the maximum and minimum values because the furnace and heat exchanger were not able to respond rapidly enough. Thus, a more responsive plant would be easier to control. By responsive, we mean that the controlled variable responds quickly to adjustments in the manipulated variable. Also, a plant that is susceptible to a few disturbances would be easier to control. Reducing the frequency and magnitude of disturbances could be achieved by many means. A simple example is placing a large mixing tank before a unit so that feed composition upsets are attenuated by the averaging effects of the tank. Many more approaches to designing responsive processes with few disturbances are covered in the book. Measurements. Naturally, a key decision is the selection and location of sensors because one can't control what is being measured. The engineer should select sensors that measure important variables rapidly and with sufficient accuracy. In this book, we will concentrate on the process analysis related to variable selection and to determining response times and accuracy needs. Details of a few common sensors are also presented as needed in exercises. A full review of sensor technology and commercial equipment is available in the references at the end of this chapter. Final elements. the engineer must provide handles, manipulated variables that can be adjusted by the control calculation. For example, if there were no valve on the heating fluid in figure 1.5, it would not be possible to control the process fluid outlet temperature. This book concentrates on the process analysis related to final element location. We will typically be considering control valves as the final elements, with the percentage opening of these valves determined by a signal sent to the valve from a controller. Specific details about the final element to regulate flow of various fluids, liquids, stream, slurries, and so forth are provided by references noted at the end of this chapter. These references also present other final elements, such as motor speed, and are used in the process industries. Control structure. The engineer must decide some very basic issues in designing a control system. For example, which valve should be maintained and manipulated to control which measurement. As an everyday example, one could adjust either the hot or cold water valve opening to control the temperature of a water in a shower. These topics are presented in later chapters after a sound basis of understanding the dynamics and feedback control principles have been built. Control calculations. After the variables and control structure have been selected, equations are chosen that use the measurements and desired values in calculating the manipulated variable. As we shall learn, only a few equations are sufficient to provide good control for many types of plants. After the control equation's structure is defined, parameters that appear in the equations are adjusted to achieve the desired control performance for the particular process. 1.8. How is process control documented? As with all activities in chemical engineering, the results are documented in many forms. The most common are equipment specifications and sizing, operating manuals, and technical documentation of planned experiments and control equations. In addition, control engineering makes extensive use of drawings that concisely and unequivocally represent many design decisions. These drawings are used for many purposes, including designing plants, purchasing equipment, and reviewing operations and safety procedures. Therefore, many people use them, and to avoid misunderstandings, symbols that are standard have been developed by the Instrument Society of America for use throughout the world. We shall adhere to a reduced version of this excellent standard in this book because of its simplicity and wide application. Sample drawings are shown in figure 1.7. All process equipment, piping, vessels, valves, and so forth is drawn in solid lines. The symbols for equipment items such as pumps, tanks, drums, and valves are simple and easily recognized. Sensors are designed by a circle or bubble connected to the point in the process where they are located. The first letter in the instrumentation symbol indicates the type of variable measured. For example, T corresponds to temperature. Some of the most common designations are the following: A for analyzer, F for flow rate, L for level of liquid, P for pressure, T for temperature. Note that the symbol does not indicate the physical principle used by the sensor. Backup tabular documentation is required to determine such details. The communication to the sensor is shown as a solid line. If the signal is used only for display to the operator, the second letter in the symbol is I for indicator. Often the I is not used, so that a single letter refers to a measurement used for monitoring only, not for control. If the signal is used in a calculation, it is also shown in a circle. The second letter in this symbol indicates the type of calculation. We consider only two possibilities. In this book, C for feedback control and Y for any other calculation, such as addition or square root. The types of control calculations are covered later in the book. A non-controller calculation might use the measured flow and temperatures around a heat exchanger to calculate the duty. That is, Q is equal to rho times heat capacity constant pressure times flow rate times temperature in minus temperature out. For controllers, the communication in the final element is shown as a dashed line when it is electrical, which is the mode communication considered in designs for most of this book. The basic symbols with their meanings are documented in Appendix A. This simplified version of the Instrument Society of America standards is sufficient for this textbook and will provide an adequate background for more complex drawings. While using the standards may seem like additional work in the beginning, it should be considered a small investment leading to an accurate communication, like learning grammar and vocabulary used by all chemical engineers. 1.9. What are some sample control strategies? Some very simple example process control systems are given in figure 1.7a through b. Each drawing contains a process schematic, a controller in the instrumentation circle, and the connection between the measurement and the manipulated variable. As a thought exercise, you should analyze each process control system to verify the causal process relationship and to determine what action the controller would take in response to a disturbance or a change in a desired value. A set point. For example, in figure 1.7a, with an increase in the inlet temperature, the control system would sense a decrease in the outlet composition of reactant. In response, the controller system would adjust the heating coil valve, closing it tightly until the outlet composition returned to its desired value. A sample of a more complex process diagram, this one without the controller design, is given in figure 1.8. The process includes a chemical reactor, a flash separator, heat exchangers, and associated piping. Note that a control design engineer must select from a large number of possible measurements and valves to determine controller connections and an enormous number of possibilities. In Chapter 25, you will design a control system for this process that controls the key variables, such as reactor level and separator temperature based on specific control objectives. 1.10 Conclusions. The material in this chapter has presented a qualitative introduction to process control. You have learned the key features of feedback control along with the types of equipment, instrumentations, and computers required to apply process control. The importance of the process design on control was discussed several times in the chapter. Based on this introduction, we are prepared to discuss more carefully the goals of process control in Chapter 2. Understanding the process control goals is essential to selecting the type of analysis used in control engineering.